Welcome to today's video on Cambridge IGCS in Mathematics for the syllabus codes 0607 and 0580. Our topic for today will be vectors and transformations, where we will be looking at the subtopic vectors. So let's go ahead and look at vector and scalar quantities. Vectors are a representation of how we can get from one point to another point. And when we describe quantities, we can classify quantities as either being vector quantities or being scalar quantities. Now, the difference between vector quantities and scalar quantities is that vectors have a magnitude and a direction specified, while scalar quantities have only a magnitude but no direction. Examples of vector quantities include force, velocity, and displacement, while examples of scalar quantities would include mass, volume, and temperature. When we represent vector quantities, there's a specific vector notation that we would be using. The general notation that you would see would be bold lowercase letters. So what we can see here are representations of vectors. When we look at scalar quantities, there's really no standard notation for representing them. You would just see them as ordinary numbers. Now, we have been given these two arrows on this on our right hand side over here, and I can say this is my vector A and my vector B. How I can say or how I can identify A and B as vectors is that they are lines that have a specific length. So I can say that's representing a magnitude. Well, they also have an arrowhead on them, which means that their directions have also been specified. So I can confirm that these are representing my vectors. So just a little bit more info into the standard notation that we can have for vectors. We've already seen one of them, and that's bold lowercase letters. When we use handwriting methods or handwritten methods, what you can actually do is you can write down your letter and then you can just underline it to represent your vector. So I can say this is my vector A. So it's a lowercase a, which has been underlined, and then this would represent vector A. We can also represent vectors by showing how your vector or how we are getting from one point to another. Now, when we represent points on the other hand, I'm just going to draw a line here. I'm going to say this is a specific vector that's taking me from point A to point B. So when we represent points, the standard notation to do that is using capital letters. So I've used capital A to represent point A and capital B to represent point B. And the vector that's getting me from A to B is AB with an arrowhead on top there. The next skill that we're going to be learning would be the addition of vectors. Now, when we add vectors, we can do this using the parallelogram, which is also called the nose to tail method. In this method, what we're going to be doing is if I need to add vector A and vector B, I can take the tail of vector B and join it to the nose of vector A, or I can take the tail of vector A and join it to the nose of vector B. Now, what is this nose and what is the tail of a vector? If I draw a vector like this, then the tip of the vector over here is called the nose of the vector. And the start of the vector that's over here, this is the tail of the vector. So let's look at an example where we're actually adding up these vectors. In this diagram, what we can see is point X and point Y. And to get from point X to point Y, I can go along two separate vectors. I can go along vector A and then go along vector B to get to my point Y from X. So what we are basically doing here is we are adding our vectors A and B. And we can see that what we've done here is we've connected the nose of A to the tail of B. We can also do this in another way that we've already spoken about. To get from X to Y, we can also go and connect the nose of vector B to the tail of vector A. And then how we would work out the answer, or what we call the resultant vector, that's the vector A plus B, is that you would connect the tail of your first vector to the nose of your second vector. So you would go from X to Y directly. And here it's the same thing. You would connect the tail of your first vector to the nose of your second vector. And this is basically the parallelogram rule, or this is also called the triangle method. You can also complete this to form a parallelogram, or you can just leave it as it is, and then this is forming a triangle. So this is how we can add vectors using the nose to tail method. Another thing that we need to understand is because we know that vectors have a magnitude and a direction, we can have negative vectors as well. And what we mean by a negative vector is the same exact vector, but in the opposite direction. So I know that we have vector A over here, which looks like this. If I have a line that's the exact same length as A, in the exact same orientation as it, so in the exact same angle, so you have a line that's parallel to A, but it's in the opposite direction to this, I'm just going to say then this should be my vector negative A. So there we go. When we're adding negative vectors, then that's basically the equivalent of subtracting a vector. So if you need to subtract a vector, then you can just flip the direction of your vector, so it turns into a negative vector, and then you can go ahead and add it as normal. Next, we're going to go ahead and look at the multiplication of vectors. We can go ahead and multiply vectors with scalar quantities, and this works just like normal multiplication. So if I start with my vector x and I want to multiply this by 2, then it's x times 2, which gives me a result of 2x. Now, if I look at this diagram here, I can see vector x as well as vector 2x. And I can see that 2x is going to be twice the length as x, but it's still going to be in the same direction. So the magnitude is doubled, but the direction has not changed. On the other hand, if I take a vector x and I multiply it by a negative vector, so in this case, we're going to multiply x by negative 3, then the multiplication works like normal. X times negative 3 is going to give us negative 3x. But if I look at the diagram here, x and negative 3x is 3 times the length of x, which tells me that the magnitude of negative 3x is 3 times bigger than x. But if we go ahead and look at the direction, because this is a negative vector, the direction here has been reversed. In addition to vectors being shown as arrows, we can also show vectors as column vectors. So we can represent them using a number at the top and a number at the bottom, and these numbers would be enclosed by more brackets. So if I look at this, this is my vector that's taking me from point A to point B, and this is going to have a horizontal component as well as a vertical component. And the number that we have at the top is going to represent the horizontal component, while the number that we have at the bottom is going to represent the vertical component. So in this case, my vector AB has the value 5 for my horizontal component and the value 3 for my vertical component. Something else that you need to remember is that if your horizontal component is going towards the right, like it's doing in this case, then it's going to be positive. And if it's going towards the left, then it's going to be negative. And if your vertical component is going upwards, it's going to be positive. But if your vertical component is going downwards, then that's going to represent a negative value. So in the case we need to add column vectors, what we can go ahead and we can do is we could just add our horizontal components together, and then we would add our vertical components. So we would do them separately. So in this example, I can see that we are adding vector AB and vector CD. So vector AB is 5, 2, and vector CD is 2, negative 3. So the first thing I would do is I would add my horizontal components. So that's 5 and 2, which gives me 7. And then I can go ahead and add my vertical components. So that's 2, add negative 3, and this is going to give me negative 1. So my answer is going to be 7, negative 1, and this is a resultant of adding my two vectors. Next, the subtraction of vectors is also relatively straightforward, and we would subtract the corresponding components of our vectors. So we would subtract our horizontal component separately, and then we would subtract our vertical component separately. Or we can even add on the negative of the vector to the other term. And let's go ahead and look at both of these methods. So just like our previous example, we're going to take vector AB as 5, 2, and CD as 2 and negative 3. So if we need to subtract these two vectors, AB minus CD, what we're going to do is 5, 2 minus 2, negative 3. And how we would proceed with this would be we would subtract our horizontal components first. So that's 5 take away 2, and that's going to give me 3. And then we would subtract our vertical components next. So that's 2 take away negative 3. And this is going to change into a positive. So that's going to be 2 plus 3, which is going to give me 5. So that's the answer for AB, take away CD. On the other hand, what I could also do is I could take vector AB and I could add on the negative vector of CD. So how I would work out the negative vector of CD is I would take CD and I would just work out the negative of this. So negative CD would be negative 2, 3. This is going to be negative CD. And you can see I've just flipped the signs of both my horizontal and my vertical components. And that's what we have here. That's the example that they've shown us here. So this is negative CD that we are adding on to AB. So we're going to work this out like previously. We're going to deal with our horizontal component separately and our vertical component separately. So this is 5 add negative 2, that's 3. And then we have 2 add 3, that's going to be 5. That's the same answer for both methods. We can also multiply vectors by scalar quantities. And if we are multiplying vectors by scalar quantities, what we do is we would take the scalar value and multiply it by our horizontal component of the vector, as well as the vertical component of the vector. So looking at this example here, they've given us vector xy, and they're told that this is 3, negative 2. And if I want to find out 3xy, then what I would do is I would multiply 3 by 3, and then I would multiply 3 by negative 2, which would give me 9, negative 6. Next, we're going to go ahead and look at parallel vectors. We say vectors are parallel if they have the same direction and both components of one vector are in the same ratio and corresponds to the components of the other vector. So if I look at this example over here, I can see that my vector AB that has been multiplied by K. So this is going to give me a vector KA, KB. And this vector would be parallel to my vector AB because vector KA, KB is a scalar multiple of my vector AB. Let's also look at another example of this. If I have a vector that's 6, 3, and then I also have another vector that's 2, 1, I can see it that my first vector, that's 6, 3, is parallel to my vector 2, 1, because this is a scalar multiple of 2, 1. How can I say that? If I divide my vector 6, 3 by 3, or if I take the component 3 out of it, then I'm going to get 2, 1. So it's a scalar multiple of my second vector. So these two vectors over here, I can see are parallel to each other. They're not necessarily going to be the same length. They're going to have different lengths, like you can see here. But they're definitely going to be in the same direction, which would mean that they're parallel. An important skill that we would need to learn when we deal with vectors is finding the magnitude of a particular vector. A We know that vectors are generally represented by arrows like this, and they would have a horizontal component as well as a vertical component. And to find the magnitude of a vector, what we're trying to do is we're trying to find the length of this line. So how we can do this is by looking at the horizontal component as well as the vertical component, and then using Pythagoras' theorem to figure out what this resultant, or what would generally be the hypotenuse of a right angle triangle, would be. And if I have vector, say, mn, where my horizontal component is n and my vertical component is n, then the magnitude of this vector would be the root of m squared plus n squared, and this has been derived by Pythagoras' theorem. Now, the symbol that we would have for the magnitude would basically be our vector that has been enclosed by two bars. So this is the magnitude of vector A. And similarly, here I can see this is the magnitude of x, because this is my vector x that has been enclosed by two bars. So let's go ahead and look at an example to help us understand these concepts. So the example reads, given that vector OA is 0, 5 and vector OB is n3, find the magnitude of vector OA and the value of n if the magnitude of our vector OA is the same as the magnitude of vector OB. So to begin with, let's start off with the first part of this question. We will go ahead and find out the magnitude of OA. Now, when we're finding out the magnitude of a vector, like we've just seen, we're going to get the square root, the sum of the squares of our vertical and our horizontal components. In this case, our horizontal component would be 0, so 0 squared plus a vertical component, that's 5, that's 5 squared. And the square root of this would give us the magnitude of vector OA. And if we work this out, we know that 0 squared is just 0, and then 5 squared is 25. So that's the square root of 25, which I can say would be 5. So the magnitude of our vector OA is 5. Then let's work on the second part of this question, where we need to find out the value of n, given that the magnitude of OA is the same as the magnitude of our vector OB. So because we found out that the magnitude of the vector OA is 5, this means the magnitude of our vector OB is also 5. So I can say that OB and the magnitude of this, which is basically the square root of n squared and 3 squared, is also going to give me 5. And what I'm going to do at this point is I'm just going to solve this equation to find out what n would be. So to begin with, I can square root out of my equation, and this would get rid of the square root over here. So end up with n squared plus 3 squared. And then I would expand all of these values to be, that's 25 to 5 squared. I can take this 3 squared, bring it to the right-hand side. It's going to change it to negative 3 squared. That's essentially 9, so negative 9. So n squared would be 25 taken to 9. Then I would have n squared is 16. And to find out n, I can square root 16. And this is going to give me an answer of 4. So there we go. N would be 4. And the magnitude of OA is going to be 5 for this question. So next, let's go ahead and look at an exam type question that deals with vectors. So the question reads, the diagram shows a regular hexagon A, B, C, D, E, F, center O with vectors OB as A. So my vector OB here is the vector A, and vector ED is B. And it asks us to find an expression for the vector AC in terms of my vectors A and B. Now, I know that my vector AC is basically any way or any method that I can use to get from my point A to my point C. And this can happen in so many different ways. I can get to A to C like this, following the yellow path over here. I can get to A to C in any other way that I like. I can go like this, following the green path over here. So it doesn't matter which path by taking, I just need to make sure that I start at A and I end at C. And every time I do that, every time I start at A, end at C, it's going to give me the exact same vector eventually once we simplify it down. So because we've been given this vector A and B, what I'm going to try to do is I'm going to try to incorporate these vectors to get from A to C. So to begin with, I'm going to start from getting from A to B here. And if I look at my vector AB and my vector ED, I know that because this is a regular hexagon, the line AB is parallel to the line AD, and it's also the exact same length. It's the same magnitude, which means that the vector AB is the exact same as my vector B. This is also going to be the vector B. So in that case, AB is my vector B. Then I can move from B to O. If I'm getting from B to O, this is the opposite of my vector A, which is going from O to B. So if I need to go in the opposite direction, it's the same vector, except it's negative A now. It's going to be the negative A. So A is from O to B, and negative A is from B to O that I've gotten here. And then finally, what I can do is I can introduce another vector here. I can figure out this vector taking us from O to C. And because this is a regular hexagon, this is kind of easy. I know that to get from O to C, it's going to be the exact same vector B again. These two lines are parallel to each other, and they also the same magnitude. So this is also going to be my vector B. So to sum it all up, to get from my vector AC, what I'm doing is I'm taking my vector AB, adding on my vector BO, and then adding on my vector OC. So the path that I'm choosing to take for this example is AB, then BO, and then from O to C to get my vector AC. So I know that AB is my vector B, and then BO is my vector negative A, and then OC is just B. And if I just go ahead and add these up, it's basically going to give me 2A. So 2B minus A as my answer. There we go. That's the answer that we have over here for our vector AC. And that's all we have on today's lesson on vectors. Thank you.